Okay, guys, I think we left off here talking about calculating pH or of a weak acid or weak base. And unfortunately, this brings us back to equilibrium, which many of you struggled with. You're going to have to use your rice tables. You're going to have to figure out what your initial is, what your change is, and then you're going to have to figure out what your equilibrium is. So this is just a special case of equilibrium, and it deals with acids or bases. Instead of using K, we use Ka or Kb depending on the type of species we have. And I did a video yesterday that should help you with working these problems. I plan on doing a couple more today just to give you a well-rounding in this area. So please make sure you watch that video, etc. So when we talk about acids, we're worried about their strength, then we have to look at their structure, because their structure will tell us a lot about how strong or weak we expect them to be, especially when comparing 2 or 3 to each other. So some acids are stronger, and acids are all proton donors. And so if we could make that bond between the acid and the hydrogen more polarized, then we can make it a stronger acid. And so we want to be able to break that bond easily, and that'll make it a strong acid. So as we get to more electronegative elements, typically acid strength increases. However, HF is not a strong acid, and please write that down. HF is a weak acid. And that's because fluorine is so small that it's very hard to stabilize that negative charge. And one of our strongest acids would be HCl. So, more compounds that can contain oxygen and one or more hydroxyl or OH group, then we look at the bond A between everything else and the oxygen, and that will have an effect on bond B. So the compounds can be acidic or basic or amphoteric. Or amphiprotic. We know that water is amphiprotic, and it has a hydrogen, oxygen, hydrogen. It can either accept a hydrogen or donate a hydrogen, depending on what's with it. And so we're going to look at the electronegativity of element E to determine whether it'll be an acid, a base, or amphiprotic. So if the electronegativity of E is low, then bond A is polar or almost ionic, and then we would have OH ions released. This would be something like sodium hydroxide. The compound is basic, and metals have very low electronegativity values, so metal hydroxides tend to be basic. That's pretty straightforward. If electronegativity of E is high, then bond A is covalent. Now the electrons in bond B are pulled towards the electronegative end of this molecule, which is where E is. And so bond B is polar, it's weaker, and it's easier to break. If it's easier to break, then we can generate hydrogen ions in solution, and so this would be an acidic compound. And these are things that are nonmetals that have relatively high electronegativity values. So if E is somewhere in the middle, it's not real metallic, it's not real non-metal in nature, it's got an intermediate electronegativity value, then this species will be amphoteric or amphiprotic. It will, in the presence of a strong acid, work as a base. In the presence of a strong base, it'll work as an acid. So metalloids and elements near the metalloids have intermediate. So aluminum hydroxide, if it's in base, it would accept, or it would donate a hydrogen ion, and it would act as an acid. If it's an acid, it would accept a hydrogen ion and create aluminum hydroxide with a plus sign, And so I'd like you to try and figure out these. You can look them up in your book or you can look them up on the internet. Complete those and see how they work. You have several homework problems that deal with this as well. And basically, these are things that we just have to look at what the context is to determine what it is. Water is the same way. If water is one of your reactants, you have to figure out if it's with a base or an acid. So I'm pretty sure you can do this. And I've worked out all the answers, and I'll be posting those later. So, polyprotic acids. When we have more than one hydrogen on an acid, like H2SO4, H3PO4, then we deal with one hydrogen at a time. We remove one hydrogen, see what the products are, and then that anion from our acid becomes our starting material for a new reaction. We write that right below it, and so we would disassociate that. Acids that have more than one ionizable hydrogen atom are called polyprotic. If I tell you that something is monoprotic, I'm telling you there's only one hydrogen that comes off, no matter how many hydrogens are in that structure. So the Ka value becomes smaller with each hydrogen we take off. They get weaker and weaker. In fact, H2SO4, the first hydrogen comes off, is strong, but the next one is very weak. So, diprotic acids. Write an example of a diprotic acid. I would suggest H2SO4. But not only do I want you to write H2SO4, I want you to write how it dissociates and get two different reactions for that. An example of a triprotic acid is H3PO4. And there I would like you to write 3 equations for the dissociation of each hydrogen individually. So we're going to stop here. I think we've had plenty to chew on for today. And have a good day. This should be about it. Thanks.